My name's Dobyns, and I'm a physicist. I've been working at the Princeton Engineering Anomalies Research Program for many years. We're looking at various effects that are anomalous because they're not predicted by current theory and nobody understands them very well. Primarily, they're the effect of human intention on random physical devices of various sorts, and the apparent ability of human beings to acquire information at a distance without the use of the known senses. These are, of course, two basically independent experimental efforts. As for the topic of this conference, of retrocausation and the notion that the future might somehow be able to affect the past in some way and to some degree, that's obviously quite relevant to our experimental program, and I was in fact able to present some experimental data here, because first, in the remote perception program, there's a substantial portion of the data where a human operator was able to describe a specified scene, an event, before it had happened. And secondly, in the human-machine experiments, there is a small but important body of data in which the action is apparently retroactive. The machine was run first, and then hours later, a human operator who was at a great distance away and working from a later time attempted to exert an intentional influence on the machine, and we still see an effect in those circumstances. In fact, it is comparable to the effect we see when the operator is right there trying to change what the machine is doing.
Is that a published result?
The published results on the human-machine experiments as a whole are in, except for our most recent experiments, are in a series of articles in the Journal of Scientific Exploration. There are some early results in a 1981 issue of the Proceedings of the IEEE, but that's really just when the program was taking its first baby steps. And as I said, some of our latest experiments, we're still working on the reduction and analysis and writing the paper.
Okay.
The specific retro-PK, as we call it, the experiments with the effect apparently happening before the intentional effort that caused it, has not hitherto been published. It will be coming out shortly, basically because we hadn't cut up our data in that particular way. We started with the local experiments and the remote experiments, and then in the remote experiments the remote experiments are the ones where, in general, the operator's not there. The operator's doing it from a distance. The remotes also subdivide into the on time, where it's just like in the lab except for the operator being elsewhere, but the machine is run at a specified time and the operator is trying to influence it right at that same time from wherever they are, which may be thousands of miles away. In the off time, the operator does their intentional effort whenever they see fit, before, after, and we had not previously systematically divided that into the sessions where the operator was doing it beforehand and the sessions where the operator was doing it after the data had been recorded. When you pull out the subset where the effort came after the data, we find that it's still a strong effect. It's just as large as, if not larger than, the other versions.
How large are these effects? How measurable are they?
They do require a certain amount of statistical compilation to work up. The average effect is a shift in probabilities of about 1 part in 10,000. Maybe if you've got a really good operator or a well-favored experiment, it may be 3 or 5 or even 10 parts in 10,000. But what we see in these experiments is not, for instance, going to beat the house advantage at any casino.
Okay. And you mentioned the Thorpe paper.
It's a Thorne
yeah,
paper, and he's actually the third author listed, although he's probably the senior investigator and certainly the most eminent person involved in that research. That's Kip Thorne, who actually popularized this work in a book called, let's see if I can remember the title, Black Holes and Time Warps, Einstein's Outrageous Legacy, which he published. It's a mass market book. It's very readable, very understandable, and I would recommend it without reservation. Dates back to 1993, as I recall, about 2 years after he published the technical article in Phys Rev.
What did it say? What was the...
The basic feature of the technical article was examining the notion of time paradox because Thorne's research group had been looking at the notion of traversable wormholes, which are a speculative feature of general relativity. They may exist, they may not.
But they don't violate the principle.
They don't violate the basic principles, so as far as we know, they're possible.
Okay.
And one of the things that emerged from their analysis was that in some cases it may be possible to create a wormhole that is not an instantaneous connection through space alone, but also through time, that has a past mouth and a future mouth, if you will, that anything goes in the future mouth comes out the past mouth before, from an outside observer's perspective, before it went into the future end of the thing.
And what are those conditions that would allow that to happen?
You would either have to start with a wormhole with a time-like connection and somehow increase the delay, or you could start with a wormhole with a space-like connection and use relativity to basically slow down the rate of time flow experienced by one of the two ends of the wormhole. Because on the inside, they're always connected and share the same time flow. But on the outside, the rest of the universe will see a different time flow if one of them is moving relative to the background of the galaxy and the cosmos, and the other is not. So that if you used, for example, a high-speed relativistic starship to send one end of the wormhole off on a relativistic trip and then bring it back, this is the twin paradox of special relativity. The one who stays at home experiences more time than the one that went away and came back. When you've got the thing back, then there's one wormhole that for which 10 years have gone by since it was built 10 years ago. That's the stay at home, and one for which only 1 year has gone by.
Right.
If you send something into the 1-year-old mouth, it'll emerge from the other mouth when it was one year old, that is 9 years ago.
And what's the other form?
The other format is that it might be possible for a wormhole connection to be established where the separation is already time-like, already goes through time rather than space, with the kind of delay lag that I just already mentioned, except that the most likely way for something like that to be established would be to have a microscopically short time interval, and so you'd need to do the same trick of sending one of the ends or openings or mouths off on a relativistic trip to increase the time gap between them.
Would the cost of this wormhole vary with the mass of the information or the material sent through it?
Not particularly. There are some tricky issues about conservation of mass with regard to things entering and popping out of them that I don't pretend to understand. Okay. But given that most of the models for constructing a wormhole involve literally astronomical masses, then the relative cost of shipping a package or a spaceship through would be essentially negligible by comparison.
But if you were sending bits of information rather than little green men with clipboards, what would be involved in that? Could you reduce the cost of the wormhole?
In principle, if you could build a microscopic wormhole, then you could send information through it with a laser or something, and the whole thing could conceivably be very cheap, but one drawback to that is that at least the Thorne style of wormhole not only involves astronomical mass, but astronomical distance scales. The current best hypothesis for how it might be possible to build one involves artificial structures the size of planets or maybe planetary orbits, depending on how you do the math. So these would be huge things. I mean, there is some speculation that you can build wormholes with a different geometry on a much smaller scale, but these all require some form of exotic matter that has rather peculiar energy density properties, and we cannot at the moment guarantee that any such thing exists.
Are there any other retrocausal communication channels, experiments or theories?
Experiments, yes. If you are willing to accept the now fairly extensive body of data that has emerged from psi experiments, from experiments like the ones that we do at PEAR, from the field of at Princeton Engineering Anomalies Research, where I've been working. The science of parapsychology has accumulated a fairly extensive body of evidence on the subject, with overall there's tremendous statistical evidence for the existence of some sort of retrocausal effects in terms of the kind of experiment where you can just set up some apparatus on a lab bench and see what it does. For retrocausation, those are much fewer and farther between.
Are there paradoxes involved in this that would keep us from observing them?
Not absolutely, no. That gets back to the Thorne paper that I was discussing earlier. Having developed this construct of the traversable wormhole, realized that it could in principle lead to a time machine, they decided to take a serious look at what happens if you have a time machine, because generally physicists have been sufficiently disturbed by the concept of time paradox that anything that looked like it led to a time machine, they decided it was unphysical and we needed to ignore it. They took it seriously and examined it by setting up a situation which would lead to a time paradox. Now, there's an issue of free will that tends to get in the way of intelligent discussion of such things, so to avoid that, they made it essentially a mechanical system where you send a projectile through the wormhole pair on a course such that it will knock itself off course by emerging earlier in time and colliding with its past self. This is basically a pure paradox. It's a series of events that's inconsistent with itself. It happens if and only if it doesn't happen. What they found is that anytime you try to set up that kind of situation, no matter how you go about the details, there is always what might be called an adjacent situation, a very similar series of events that is self-consistent and that can happen. In this case, the simplest examples are you shoot in the projectile on schedule, you see a projectile emerge from the early mouth at not quite on the course that you planned for it. It makes a grazing collision with its earlier self, just enough to knock itself onto the course that it actually travels through the wormholes on. And now you've got a nice self-consistent situation and no paradox.
Okay.
Now, there are some technical elaborations on that you ultimately have to invoke quantum mechanics to solve, but the basic answer is that paradoxes cannot happen. There is always an alternative, which may seem rather unlikely and contrived, but at least as I see it, you can boil down the whole analysis to an aphorism. Once you eliminate the impossible, whatever is left over, however unlikely, must happen.
I see. You talked about free will earlier in the three cases, or want to explain that a bit?
Well, generally, people talking about time paradoxes usually have something like a human time traveler going through planning to do something stupid like interfere with his own past self and prevent something from happening which he has already experienced. And this creates a much more complicated problem because there's the issue of what a person wants to do, what a person decides to do, and these are all issues that physics as such is not really qualified to talk about at the present time. So that's why to develop a physical solution to the question of time paradoxes, it's a good idea to avoid having a free-willed agent, avoid having a complex system, just make it very simple and direct and see what happens.
Okay. Great. Anything else you want to talk about? That's very good information. It's very succinct, and you've explained the wormhole quite well. Anything more about wormholes that you think might?
Well, they remain speculative, and there are theoretical ways in which they might be constructed, but there's still a great deal of disagreement among physicists as to whether any of those theoretical ways are actually implementable.
Is there any possibility that wormholes could already be happening in ways that we don't understand and that we just don't have the physical knowledge of how they would work?
Some interpretations of quantum gravity suggest that the space around us is constantly riddled with submicroscopic wormholes that exist only for infinitesimal fractions of a second and connect regions that are only separated by minuscule distances and time intervals.
Yeah.
Other interpretations of quantum gravity say that that's not happening. So this is, again, very much an open question and waiting for further refinements of theory and experiment.
Can I ask what your background is, educational background and work experience and such?
My educational background is that I am a theoretical physicist. I got my PhD from Princeton University in 1987, and I have spent most of my professional career working at the Princeton Engineering Anomalies Research Program.
So you're within the established academic milieu, working on topics that are, some might think of a little fringy. But
that would be a fair summary. Most of my professional publications have been on this rather exotic research, so I don't exactly have a big reputation in the conventional mainstream. But
you came through the conventional mainstream PhD program.
Absolutely.
And you know physics as done in the current science.
Yes.
And you've chosen to move into the anomaly research model.
Yes.
Can you talk a little bit more about the conference and the symposium, other interesting things that you found that would be interesting to people that are not PhD physicists?
Well, there were a good many excellent presentations. Avi Ilitzer, who is a real world-class physicist and I think one of the greatest minds of our current generation, presented a long talk on what might be called quantum paradoxes, which are bizarre effects that emerge as consequences of quantum mechanics, that a lot of the stuff that he was talking about was orders of magnitude beyond the problems and the unexpected effects that you learn about in like an introductory physics course. It would take a fairly long time to explain them all, but to give an example of the kind of flavor, there was a result in the popular press that received some circulation recently, that people working on building quantum computers have discovered that you can actually get a quantum computer to give you the answer to a calculation without actually running. Well, Avi's stuff is like that, only an order of magnitude weirder. And at the moment, it is all theoretical work. It is firmly grounded. It is absolutely clear that this is what the theory of quantum mechanics predicts and requires, but for the most part, people have not yet run the experiments to test it. Yeah. However, thus far, quantum mechanics has passed every experimental test, so there's every likelihood that when somebody gets around to doing these experiments, they'll be just as strange as Elitzur has predicted.
And going from the quantum level to the computer spitting out a report on a printer, there's a huge scale difference, macro versus micro, whatever. How do you go from the quantum effects and time zero being indefinite or whatever, to the real world that you and I are talking in? Is there anything that gets lost in that scale translation?
Depends on what kind of quantum effect you're talking about. For instance, computers only run because of quantum effects. They're all based on semiconductor logics, which wouldn't work if not for the quantum properties of matter in the solid state. Now, it's possible that I'm not speaking with absolute correctness here. There may still somewhere out there be a few computers based on vacuum tubes for which that's not true. But if you've got a Pentium or even an old TRS-80 running, it's a quantum device. Yeah. Now, the quantum computers that I referred to are a little bit fancier than that, because they don't just exploit quantum mechanical properties in order to function. They actually store their data in a state of quantum superposition and conduct their calculations in the same way. So that in essence, they are probing every possible solution to a problem all at once in a single step. This is why people are eager to pursue them.